On behalf of Shri Vaishnav Vidyapit Vishwavidyalaya, I, Varsha Pathak, member of Science Club, feel privileged to welcome you all to expert lecture on porous organic polymers towards a sustainable future. Light symbolizes knowledge and divinity. It not only dispels darkness, but also illuminates our souls. Before beginning the event, let us start the beginning of blessing of Goddess Lakshmi, the Goddess of Knowledge. I request the technical team to kindly play the AV for Saraswati Vandana. Thank you, sir. Today we are honored to have with us Professor Suman Mukhopadhyay from
ब्रह्माच्युत शंकर प्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा.
Today we are honored to have with us Professor Suman Mukhopadhyay, Department of Chemistry from Indian Institute of Technology, Indore, as a distinguished speaker. Let us extend a gracious welcome to our guest. I request our technical team to play the AV. We welcome you, sir. Now I request Honorable Vice Chancellor Shri Vaishnav Vidyapit Vishwavidyalaya, Indore, Dr. Upinder Dhar, to deliver the welcome address. Over to you, sir.
Good afternoon to all of you. At the outset, I am very happy to welcome Dr. Suman Mukhopadhyay from IIT Indore.
Thank you, sir.
Well, all of us believe here in Shri Vaishnav Vidyapit Vishwavidyalaya that it is necessary to have scientific temper. We need to learn, but then at the same time have a scientific temper towards our experiences. Our science club has been organizing various activities from time to time, and lecture series, which is basically for this lecture series, we invite eminent people from the science discipline to share their experiences, share their research with all of us, and enlighten us with the contributions made by them. The intention is to remain up to date and know more about the work done by our scientists in the country, so that we can take it forward, and some of us can get inspired and work in the area of their interest further. So, not taking much time, I once again welcome the distinguished speaker today, and I'm sure that all of us will not only enjoy the whole session, but will also learn in the process. Thank you very much.
Thank you, sir, for this enriching address and valuable information. Now I would like to invite the coordinator, Science Club SVV, Dr. Asmita Sharma to introduce our distinguished guest, Professor Suman Mukhopadhyay. Over to you, ma'am.
Thank you, ma'am. Dr. Suman Mukhopadhyay is Professor, Department of Chemistry from IIT Indore. He has been engaged in teaching, research, and consultancy for the last 25 years. He has widely published his research work and has more than 80 publications in the national and international journal, and one patent to his credit. He has served as Head Department of Chemistry, IIT Indore, Dean Planning, IIT Indore, Head Center of Biosciences and Biomedical Engineering, IIT Indore, Head Sophisticated Instrument Center, IIT Indore, ex-member, Board of Governors, and Board of Studies, SJSITS Indore. 15 research scholars have been awarded PhD degree under his supervision. He has been on the panel of reviewers of many renowned journals. He has presented papers in several national and international conferences, seminars, and had opportunity to visit Switzerland, Portugal, United States in connection with various professional and academic assignments. Dr. Suman had coordinated many projects on the polymer, which was funded by CSIR DST. He has completed the research projects on exploring lithium-based metallodimers for improved anti-cancer activity and mode of action, Indo-Valeria Joint Project. He has also been principal investigator for studies on targeted organometallic anti-cancer drug and their mode of action, and nano-size material anchored by metal complexes catalyst, synthesis and application in hydrocarbon oxidation and hydroisomerization reaction in the Porous Joint Project from DST. He is life member of Royal Society of Chemistry, American Chemical Society, and Indian Association for the Cultivation of Science. He has received postdoc fellowships from National University of Singapore, Instituto Superior Técnico, Portugal, and Marie Curie International Incoming Postdoc Fellowship, Switzerland. May I request you, sir, to address the gathering?
Thank you, madam, for your kind introduction. And thank you, the Science Club, Sri Vaishnav Vidyapith Vishwavidyalaya, for inviting me to present some of the work which is going on perhaps around the world to mitigate the concern of environmental pollution and to make the world more sustainable. So that is a burning issue nowadays, and we can feel it well even in December. We don't see that much of cold. Perhaps that is an effect of global warming, we don't know. So let me try to share my screen, and please let me know if the screen is visible so that we can take it further forward. Is it visible, madam?
Yes, sir, it is visible.
Okay, fine. I'm going to the full screen mode. I hope it works. Is it okay?
Yes, it is
Yes,
okay.
sir.
Okay, fine. Thank you very much. So today our topic is porous organic polymers, or POPs. You can say it's a nickname, towards the sustainable future. Now, sustainability is a term which we are hearing nowadays quite often. And it is more important because our world is facing the challenge of keeping it habitable for the next few decades. I think there will be a lot of efforts to be given for that. And regarding that, the sustainability, if you go for the definition of sustainability as per the United Nations document, it talks about the development that meets the needs of the present without compromising the ability of future generations to meet their own needs. That means we should restrict ourselves up to that amount of resources to utilize for our own benefit, so that we leave behind something for the future generations. Now, when we talk about sustainability, the first thing comes to our mind is environment. And a lot of talks are going on regarding the environment nowadays. But we have to also remember that sustainability is not only about environment. There are two other factors which is also going to contribute in terms of sustainability: economic sustainability and societal sustainability. So if we look at the environmental aspects, definitely the goals are going to be ecological integrity to be maintained. All of Earth's environmental system are kept in balance. I am giving some kind of stress on this particular term, kept in balance. I will come back to you later on. While natural resources within them are consumed by humans at a rate where they are able to replenish themselves. So we should not eat too much. We should make a kind of dietary chart for ourselves, so that something left behind for the future generation. Apart from these environmental aspects, there are economic aspects, like the goal is to be human communities across the globe are able to maintain their independence and have access to the resources that they require, financial or other, to meet their needs.
Excuse me, sir.
Yes.
Are you at title slide?
No.
But I think it is not changing.
Shifted. Okay. So what would be the option? Is it
Second slide, yes.
yeah, it's gone to second slide. Okay. So I am here somewhere talking about the environmental, economical, and societal impact on sustainability. And I was talking about environmental goals to maintain the ecological integrity and keep the Earth's environmental system in balance, while natural resources are consumed in a rate where they can be replenished by themselves. And I was also talking about the economical sustainability, that is basically the human communities across the globe are able to maintain their independence and have access to the resources that they require, financial and other, to meet their needs. And we have also the societal sustainability. Universal human rights and basic necessities are attainable by all people who have access to enough resources in order to keep their families and communities healthy and secure. Now, for the latter two part, economic and social, there are economists who are going to discuss about these issues. And of course, there are social scientists who are going to take care of that part. But in a program of science club, we are going to stress upon on environment, and that is very, very important. So I am taking other route to change the slide so that it is visible. I am in third slide, so it is visible to everybody.
Yes, sir.
Yes, so now we are facing a big threat. The big threat is global warming. We know about that. If you can look at the chart, you can see that it's all about the increasing temperature of the global atmosphere or Earth's surface, you can talk about. And you can see from 1960s, there are a steady increase in the average temperature, global temperature. And this is getting contributed by some gases which are known as greenhouse gases. Now, looking at this chart, you might get the kind of a feeling that we are going back to the COVID days. And we are seeing chart that how the peaks are getting asymptomatically getting increased. And we have talked about a lot about how to flatten the curve. And nowadays, again in China, they are facing a lot of COVID surge. I hope that it should not strike India. Now here also, though it is happening slowly over the years, but the temperature is getting increased and we have to think about to flatten the curve. And if you look at the reason, as I said, that it is basically happening because of emission of heat trapping greenhouse gases. What are those greenhouse gases? Carbon dioxide, methane, water molecules or water vapors, nitrous oxide, hydrochlorofluorocarbon, and ozone. All these gases are getting generated in excess, and that is creating a lot of hazard, and it is trapping the heat in form of IR, absorbing IR radiation from the sunlight. Now, the question is whether all those gases are really the villain. The answer is no. Why no? It is because of the presence of these gases in minute quantity in the atmosphere. The average surface temperature of the Earth is 14 degrees Celsius. If they were not into minus 20 degrees Celsius. So in that case, our Earth may not be that much a good place for habitation. So the key point is that we have to maintain the concentration of these greenhouse gases. And if you look at how the global temperature is increasing in different parts of the world, you will see the most of the increment is happening in the polar North Pole region. That means it is creating a lot of melting of polar caps. And the imminent threat is the level of the ocean that can get raised and further, and it can inundate very coastal area. So it can create issues. Now, it is not only about the global warming. When we talk about the pollution, it is also about pollution in different forms in terms of generation of toxic gases, which may not be contributing in the greenhouse effect, administration of pesticides, dyes, polythenes, heavy metal ions, and all of them is jeopardizing the life. And it is not affecting only the human being, but it is also affecting the whole biosphere in a negative way. So when we talk about pollution, the first thing that goes into our mind is that a picture like this, lot of fumes and vapors are coming up from the chimneys of different industries. And as this pollution is happening day in, day out, and if you look at the definition of the pollution, it talks about addition of harmful material or introduction of harmful material in the environment. So we should stop adding or introducing materials which are harmful for the environment. So there is one popular novel named Xenos. This is written by Dan Abnett. There is a powerful character who says that, but my patience is not limitless, unlike my authority. So sometimes we feel like that perhaps it is the quotation of nature. Perhaps nature is just patiently waiting that how far we can damage the environment. But definitely it will be not limitless. So it will strike back to us. So we have to do something about cutting down this pollution in some way or other. Now, as I said that it is about introducing of harmful materials in the environment. These materials are made up of molecules, different kind of compounds, and there is a huge role of the community of the chemical sciences to come forward so that the use of these harmful materials can be curtailed or can be trapped or somehow it can be decreased. So that is how it is to be going to be forward. Now coming back to the fact that we are talking about going to talk about porous materials, let us see what is porous materials. We have talked about the sustainability and environment. Let us see about what is porous material. Now a porous material is a material that contains pores, and they have some white space in their skeletal structure. So you can think about a building when there are the beams and bars and all those things, that the lattice network is there, and then comes the walls, and these walls can be fabricated in different way to get the space confined in different ways according to our need, what we want to make it. And similarly, these are the compounds which are having pores inside in the skeletal structure, and this porous material can absorb host molecule in their pores. Different kind of host molecules can be absorbed, and depending on the pore size, they can be divided into different categories like micropores, mesoporous, and macroporous. And the example of natural porous materials, we can see rock, soil, bones, cork, etc. And this is the example, the picture you are seeing. This is about ceramic. Ceramic is available in nature. These are mostly non-metal oxide like silicon oxide or boron oxide, but there are some metal oxide can be also mixed into it. So this porous material can play a very, very crucial role to stop the pollution and to help us to make our earth sustainable. So let us see how it is working. So let us go to the next slide. Now, as I said, that based on the pore size and composition, we can divide the porous material in different ways. If you look at the pore size, so you can see that we have macroporous material where the diameter of the pores are more than 50 nanometer. There are mesoporous material which are having diameters of the pores between 2 to 50 nanometer. And there could be microporous materials which is having mostly the pores which are less than 2 nanometer. So as the size of the pores becomes smaller and smaller, so the surface area becomes larger and larger, like a finely divided material. If you divide it in a very small part and go to the nano level, the total surface area becomes very, very high. Similarly, if the pore size decreases, definitely the total surface area becomes higher. And if you look at composition-wise, there could be natural polymers, natural porous materials like cellulose, and there could be, of course, synthetic porous material, which we are going to discuss a bit about today, that how the synthetic materials are coming up, porous materials, which can help us to mitigate the environmental problem. Now, modern world needs upgraded material or upgraded porous material. It starts from clays. We know it is naturally existing and it is porous in nature. In 1930s, it has been found that we can prepare aluminosilicate gels, which are having pores inside them. In 1947, the microporous carbons was discovered in form of charcoals. In 1948, synthetic zeolites gets introduced, having pores inside that. After then, after 50 years or so, there is no further new porous material. In 1995 onwards, there comes the metal organic frameworks or porous coordination polymers, having huge pores inside them, which is comprised of metal ions and some organic molecules as linkers between the metal atoms, and there are pores inside. And then in 2005 onwards, it came the porous organic polymers or organic frameworks, sometimes it is named as, and it has started almost in 2004-2005 with some seminal work of Omori Yagi from University of Michigan, which we are going to see in next few slides. But before going to there, I must also talk a little bit about the conventional polymer, which is made up of mostly covalent bond, where monomeric units are linked by strong covalent bonds and have excellent properties as materials. However, high temperature and pressures are typically required for processing due to polymer entanglement in highly viscous cement. So these are some examples of this kind of polymers based on silicon. And then you have some supramolecular polymers where apart from this covalent bond, there are hydrogen bonds among the different parts of the molecules, making it more flexible. So these supramolecular polymers are polymeric arrays of monomeric unit, and they are connected by reversible and directional secondary interaction. These secondary interactions could be hydrogen bond, could be van der Waals interaction, could be ionic interaction, could be pi-pi stacking, and all those kind of interactions which are softer in nature, imparting a lot of flexibility in the structure of the supramolecular polymers. Now, going further forward, so this is the work I was talking about, reported by Omar Yagi in Science, where you can see that boronic acid, they can be utilized together to form a triangular unit by dehydration. Now, they have used only organic material mostly because they want to make some porous material which are lightweight. If you use metals, the weight becomes higher, but they want to make some lightweight porous material. And when this diboronic acid is treated at high temperature, and it comes about a polymeric structure with pores, and you can see the pore size or diameter is something like 1.5 nanometer or 15 angstrom. They have given the name of this compound COF1 or covalent organic framework 1. And they found that surface area of this particular porous material is about 700 meters square per gram. And when they used the same diboronic acid to react with hexahydroxytriphenylene and did some dehydration reaction, they get bigger pores with the pore diameter is about 27 angstrom, 2.7 nanometer. They have given the name as COF5, and the surface area, we can see it is about 1590 meters square per gram, which is quite high in nature. So they published this work in the world famous journal Science in 2005. And there starts the beginning of the covalent organic framework. Going further forward. Now, when we talk further about this covalent organic framework, we see that they can be of two types. Now, this is also known as porous organic polymers. They can be amorphous in nature, or they can be crystalline in nature. When it's amorphous, where the atoms and molecules are not organized to definite pattern, this is known as amorphous, such as solids include glass, plastic, and gel. And crystallines are when their arrangement of the atoms are highly ordered and the molecules in the microscopic structure, they are known as crystalline structure. Now, what kind of effect on this amorphous nature or crystalline nature is there? In crystalline molecules, they are basically highly specific surface area is there, and there is precise pore size distribution. Whereas, and there are three-dimensional channels also in the crystalline porous network. But in amorphous compound, what you will find that it is much more stable in room temperature, but the pore width are not uniform. They are of different sizes. So there are hierarchical pore sizes available in the amorphous solid. So these two kind of porous organic polymers, they have different properties, and accordingly they can be used for different kind of application. Now, why these POPs or porous organic polymers because they are formed by covalent bonding. So generally, they are chemically very stable, thermally very stable, so it can be utilizable. The pore size you can tune with different linkers. The porosity, type of porosity can be also changed. The shape of the pores can be also changed, or it can be tuned. And the compound can be highly crystalline. So it has been found that mostly if the compounds are formed by thermodynamically driven compound, it forms crystalline structure. But if you make it a kinetically driven reaction, generally you obtain amorphous structure for that. Now there is a beautiful review article which gives the idea of the structural diversity in covalent organic frameworks. You can have these hexagonal structures, you can have tetragonal structures, you can have star-shaped, you can have rhombus-like structures here. So many beautiful structures can be obtained for this covalent organic framework. But one thing we need to remember is that these structures are mostly obtained through optimization of the structure. Actual structure cannot be obtained because these compounds are mostly insoluble in nature, precipitates out from the reaction mixture easily. So growing crystals to get the actual solid state structure is very difficult. So mostly the structures are theoretically getting optimized. Now, how the POPs are getting formed? What are the different methods? What are the strategies? The first is solvothermal strategy. Solvothermal strategy is basically you put the reactants in a closed vessel and you heat them at high temperature for long period of time and you get your product. Generally, you get good crystalline product, and the solvent you are using for the reaction can affect the structure. The second strategy is mechanochemical strategy or mechanochemical synthesis. You mix the ingredients together in a mortar and you grind it to the vessel for long period of time, and the ingredients react in the solid state and you get your product. Generally, it is fast and environmentally friendly because you are not applying any heat. However, the product is poorly crystalline and specific surface area is found to be less. There could be microwave assisted solvothermal synthesis. You put your reactants in a test tube like tube, a special tube, and you put it in a microwave reactor and you heat it. You'll get a fast heating rate in microwave oven, and generally you need a polar solvent to work in the microwave environment and you get your product. The fourth synthesis is ionothermal synthesis, where generally you use some ionic liquids as a solvent and you can go to a very temperature, high temperature, harsh reaction condition can be obtained. The compound you generally get is thermally stable. And the fifth is post-synthetic modification. That is, once you get your porous organic polymer, you can further modify it by changing the some functional groups with further reaction. So that is the way out to get your porous organic polymers. And when you are trying to synthesize porous organic polymers, you can use different type of linkers like this borazine, boronic ester, beta-ketoamide linkers, azine linkers, imine linkers, hydrazone linkers. So these kind of linkers are available to us so that we can make our porous organic polymer compounds. To go further forward, let us see that once you get your compound, how you are going to characterize them. So to characterize the compounds, we have to remember the compounds are mostly insoluble in nature. So we have to depend upon on various analytical tools and mostly microscopic tools so that we can get an idea about the structure of the synthesis compound. You can get through SEM, that is scanning electron microscope, where you can get the morphology, TEM, tunneling electron microscope, and AFM. It can give the skeleton structure. FTIR, and that helps us to understand what kind of bond groups are present there. Solid state NMR, that can give us an idea about the atomic connection. ADS, that gives the elemental composition of the compound. Powder XRD, it gives the crystallinity or crystal structure. And BET, that gives about the pore size and the specific surface area of the compound that we have synthesized, and we can get some idea about that. So these are certain examples. This is solid state NMR. In solid state NMR, we don't get sharp peaks, we get broader peaks generally. This is the scanning electron microscope, which can give the morphology of the synthesized compound. How does it look like? There it was a button-like structure. We have powder XRD. So the optimized structure, we can simulate the powder XRD pattern, and we can get the powder XRD data to see that if it is matching well with the simulated pattern. Then we have the bed isotherm. Sorry, I am still in the slide number 15. So then we have BET isotherm, which gives us the foresight when we calculate the nitrogen uptake with the increasing partial pressure of the gases. This is EDS spectra giving the elemental composition, tunneling electron microscope giving us the internal structure of the compound, and FTIR talking about the different bonds present in the compound that is getting synthesized. So the question is that what is then the application for the porous organic polymer? These can be utilized as they are free space. It can be utilized for gas adsorption, energy storage, semiconductor, as a catalyst material, and a photoconductor, and water treatment. So there are different kinds of applications where you can use covalent organic framework or your porous organic polymer. So let us see how they can help us. Now this is again the different areas where this covalent organic framework can be helpful. Now if we take the consider catalysis, so we know the catalyst is generally helps to reduce the activation energy. So if you see if we plot this energy profile diagram, in x-axis it is reaction coordinate, and in y-axis it is the energy. You can see the reactants, they have certain amount of energy, and when it is going to the product, it is having certain amount of energy. But the path it is taken, it is a steep high energy path to reach the transition state, and then only it can come back to the product. So it requires amount of activation energy, and that activation energy is generally supplied by heat. Now, if we use some catalyst, this activation energy can be reduced, as the catalysts are going to be giving an alternative pathway for the reaction to follow. So in that way, we are saving some energy. So it is becoming much more environmentally friendly. And suppose after addition of the catalyst, if we don't need to heat at all, but we get the energy from the sunlight, then it becomes more environmentally friendly because we are not using any heat at all. So this is the area, that is the photocatalysis, that is getting a lot of attention these days. You can see that this is one example where they have picked, say, some triazine covalent organic framework, which can absorb the sunlight in the range of 504 nanometer with a band gap of 2.46 electron volt. And the COF, the polymer, gets excited. The electron goes from lower energy level to the higher energy level. And in this way, through the charge separation, the higher energy level electron can disintegrate different dyes. Dyes are utilized in garment industry, but you can see that these are harmful, and this is discharged in the water bodies. So treatment of the sewage for this industry is important. And the best way is that if you can disintegrate the dye with the help of sunlight and photocatalysis. And they have found that that can be done with the help of their covalent organic framework, rhodamine B. RHB that can be disintegrated through radical pathway when it is treated with this kind of catalytic covalent organic framework, and that helps a lot. Also, I would like to draw your attention about the energy. Green energy is an important part that is also to be taken care of, because whatever energy demand nowadays we are facing, that is getting totally mostly that is getting compensated through the burning of fossil fuels, and that is creating generation of a lot of carbon dioxide. So if we can somehow manage to get greener energy, then that is going to protect our environment for that kind of pollution what we are facing nowadays. Now, this is another example which is quite interesting. Here you can see that some covalent organic framework, this is reported by Rahul Banerjee group from ISAR, Kolkata. They have made some covalent organic framework by utilizing the benzidine and then this trialdehyde, and they take all together and they mix it in a vortex shaker for a long period of time, and they make a dough, and that dough is utilized to make a membrane on the top of a glass plate, and that membrane can be peeled off, and this covalent organic membrane COM that can be taken in a vessel, glass vessel, and it can put into the bottom, and they then added two different molecules, colorful molecules. One is rose Bengal dye, which is a pollutant, and they have taken as a marker as a nitroaromatics, I think nitrotoluene, and they have added it into, and they pass this mixture of solution through this dough or the membrane, and they have taken out the solution out of that. And what they found is that the rose Bengal dye gets totally adsorbed, it is not coming out, but the nitroaromatics, that is the nitrotoluene, is only coming out. Now, what is the reason for that? You can see the mixture of rose Bengal and nitrotoluene, and then nitroaromatics, I think, and then they make a orange color. And when you pass it through this membrane, you are getting only the nitroaromatic. The rose Bengal is not coming out. It is because the covalent organic framework or covalent organic membrane, what has been synthesized, it has a pore size which is something around 1 angstrom, 1 nanometer, the diameter. Now, if you consider the size of the rose Bengal dye, that is size is bigger than that. But the nitroaromatics, they have a smaller size with 0.7 nanometer. So it can pass through the pores of this covalent organic framework. And in this way, it can help to trap the dye and allow the marker molecule to pass. And in this way, it can work wonder as a kind of a sieve, molecular sieve, to stop the rose Bengal coming out from the solution. The surface area of this covalent organic framework is found to be about 800 meters square, and the pore size is something about 2 nanometer the diameter. Now, this is another example where they have utilized some triazine-based covalent organic framework. They have got it utilizing triformyl benzene, and this is hydrazine. They have reacted both of them together to get a framework like this. They have taken hydrazine to make the spore smaller. So they have named it, this is a Chinese group, they have named it as ACOF1, and this has been utilized for the capture of carbon dioxide gas. The pore size is 0.94 nanometer. And as the pore size becomes smaller and smaller, it becomes easier to capture the gas. And they have found that they can capture the carbon dioxide gas at 273 K, that is a 0 degree centigrade, almost in 1 atmospheric partial pressure. it is capturing almost 180 milligram per gram of carbon dioxide, is quite high. And at room temperature, it is about 80 milligram per gram. So it can capture carbon dioxide. It can also capture hydrogen and methane, but they have shown that there is a kind of selectivity to capture carbon dioxide over hydrogen and methane. So this removal of greenhouse gas like carbon dioxide and methane by capturing and storing in the pores of these POPs is possible. Maybe it has not reached to the value it should be, but it is showing some progress in these aspects. And it can also store hydrogen gas, which can be used as a fuel for the green fuel. So we have started doing this kind of work in the last couple of years. So we have synthesized one such polymeric porous compound by reaction between piperazine and some triazine linker. And we get a surface area about 625 meters square and the pore size about 7.55 nanometer. And what we find is that it can selectively capture mercury ion, mercury 2+ ion inside the cavity of our covalent organic framework. And the mercury capture can go up to 1329 milligram per gram from the Langmuir plot what we obtained. So if we take our polymer and if we take a solution aqueous solution of mercury and we pass through the polymer, it absorbs the mercury specifically, and it does not allow the mercury to pass through our covalent organic framework. And it is not a framework, rather it's polymer, amorphous polymer, and we can get clean water out of that mercury containing water. When passed through this polymer, it gives a clean water. Let us go further. I think I am in which slide, sorry. Yeah. So furthermore, these polymers can be utilized for the sensing applications. Sensing means it can sense toxic gases. It can sense trace amount of toxic metals like mercury and lead. It can also sense explosive like nitroaromatics. Now, what is sensing? Basically, sensing is that if you change the color or the fluorescence of a compound, when it is in vicinity with some such kind of toxic gas or metal ion, or in such kind of nitroaromatics. So as an example, we can talk about this beautiful work. This is reported in Journal of Material Chemistry, where you can see they make a cough. And this has been made out of, again, tetraaldehyde and some aging ligand. And these coughs can sense acid vapor by change of color. What you can see that this cough material can be casted with a aerosol making with a chitosan, which is a polysaccharide. And it can be casted like a deep green leaf-like color. And if you just put a drop of HCl, add a drop of HCl, not on the top of the leaf, but within the container somewhere, and you close the lid, the acid fumes which comes out of this particular HCl bleaches the color of the leaf. So that talks about the presence of acid fumes in any place, even it could be in a closed place like a room or somewhere. And it has been sensed because when the acid vapor is not there, it forms this kind of structure which is hydrogen bonded, where this ether linkage makes some hydrogen bonding with this NH amide NH group. But in presence of acid vapor, this nitrogen gets protonated and this linkage gets clipped. And therefore the bleaching of the cut. Now, another example just I would like to share here, that is the copper absorbance of the copper ion. Here again, you see there is some covalent organic framework is formed, and this gives a beautiful red-orange color. But when you treat this covalent organic framework with copper ion, this copper ion gets attached to some place inside this covalent organic framework through covalent interactions. And the red-orange color or the fluorescence color disappears. And in this way, it is possible to detect the copper ion in a solution. The surface area of this covalent organic framework is not great, but the importance is that among the various ions, it can detect copper ion through switching of the fluorescence inside the cavity. Now, going to the last part of the application, where I would like to talk a bit about photocatalysis. As I said, photocatalysis is very, very important. In photocatalysis in a molecule, there are some electrons in the valence bands, and this can absorb light, sunlight. Electrons can go to the conduction band, and this high energy electron can react with some reactants and reduce them. And the cavity, the hole that is formed in the valence band, that can take up electron from some reactant, and the reactant gets oxidized. So this is the way the photocatalysis works. Photocatalysis is a chemical reaction which gets activated in the presence of photons of a particular energy. And these photons supply energy to the electrons of the valence band. And these electrons absorb the energy from the photons and get excited to the conduction band. And these free electrons in the conduction band now participate in the reactions. I am going to give 3 examples here. 3 last examples, all are very important. The first one is about photocatalytic carbon dioxide reduction. We are talking about greenhouse gas, carbon dioxide. It can be utilized by photocatalysis. So what they have done, they make some covalent organic framework along with nickel with a porphyrin cavity. And this substituted porphyrin cavity, in the back side, there are some nitrile groups which can further react between them to form triazine moiety. So this triazine moiety gets formed. And these nickel porphyrin groups can absorb sunlight. And in that way, it helps to catalyze the reduction of the carbon dioxide. So this is carbon dioxide uptake. As this is a porous network, it can trap carbon dioxide from the atmosphere. You can see at a lower temperature, it can trap almost 4 millimole per gram. At room temperature, it can trap about 2.5 millimole per gram. And then further, in presence of electrical impulse or under certain potential difference, these particular CTF, that is this photocatalyst, can show production of carbon monoxide from carbon dioxide, and it is having a very high Faradic efficiency, reaching to about 97% of generation of carbon monoxide at a electric potential about minus 0.9 volt. So this is the first example, reduction of the carbon dioxide. Second example is the generation of hydrogen from water. We know hydrogen is a clean fuel. It burns with oxygen, gives a lot of energy, but we have to get the hydrogen from the water. That is a cumbersome process. That is not easy. And for that, you need more energy. So if that can be done through the photocatalysis, that could be very, very effective. So scientists are trying to find out a way out so that proton present in the water can be reduced to get hydrogen gas. And to do that, this is the complete reaction. Proton gets converted into hydrogen, and the oxygen of the water molecule gets converted into oxygen. This is the whole reaction. And this can happen through the process which is called photocatalysis only when we have photoabsorber, proper photoabsorber. So what is PA? That is photoabsorber, that is absorbing light. This part, this is ACD, this is sacrificial electron donor who is giving electron. And here it is the HEC, that is hydrogen evolution catalyst. So again, what happens is that it uses a catalyst which absorbs light. Electron gets excited to the higher energy, and that electron can reduce the proton to hydrogen gas, and this hydrogen gas can be captured and can be used as a clean fuel for that. And one of such example is given here. This is a covalent organic framework into which they encapsulated an cobalt catalyst. And the idea is that to supply proton, electron to this proton to get the hydrogen gas. So this cobalt catalyst in cobalt plus 2 oxidation state, it supply 1 electron to this proton, and it gets oxidized to cobalt plus 3 state. Then it gets electron from the polymer. Okay, so it gets back again into cobalt plus 2 state. Now the polymer is now devoid of electron, and it gets the extra electron from one sacrificial reagent, which is known as triethanolamine here. So these covalent organic framework, through the presence of sunlight, can transfer electron to this cobalt catalyst. And this cobalt catalyst can transfer electron to the proton of the water to generate the hydrogen gas, which can be captured as a clean fuel. So using this nitrogen off as the photosensitizer and chloropyridine covalescent co-catalyst, hydrogen evolution rate was obtained, which is about in the tune of micromolar range, which is not sufficient yet. But if it can be given in molar range or millimolar range, it would be very much useful to cleave the water and get enough hydrogen, which can be used as a clean fuel for our necessary requirement. And this is the last example from our own work. We have made a cationic porous organic polymer. It is made out of some imidazole triazine ring and some benzyl chloride anthracene group. And you can see this nitrogen is positively charged, and this is counterbalanced by a chloride ion. Now, this presence of this chloride ion helps this particular COF, which we named as IPOC ant, as an absorber for the toxic material like chromate, dichromate, permanganate. So I am not showing that here, but rather what I am showing that these particular COF or porous organic polymer, it can absorb visible light in the range of 540 nanometer, which is equivalent to 2.58 electron volt, and that can be utilized for the degradation of the different dyes. So this is the scanning electron microscopic image of our porous organic polymer, and you can see that the rhodamine dye can be clipped utilizing the photocatalysis of our covalent organic framework. And you can see that with the time, the specific signature peak for these dyes, rhodamine B, rhodamine 6B, and methylene blue, that is getting reduced, indicating the disintegration of these dyes within our polymeric structure. So it can disintegrate up to 97% of the dye within few minutes time. So to conclude, what we can say is that the future is not looking very bright at this moment because of the devastating environmental pollution and the burning of fossil fuels, industrial and technological advancement. These are responsible for the deterioration of environmental balance. And the recent climate change is the consequence of extreme pollution in the environment. And so we have to think out of the box. The conventional approach is not good enough to rescue us from this situation. So we need some sustainable alternatives. So these porous organic polymers, which have been worked upon in last 15-20 years, not more than that, it has already shown a lot of promise as excellent sustainable alternative because of its versatile application. And it might be the right candidate to save our planet from the catastrophic consequences due to pollution and climate change. At the end, just I would like to acknowledge IIT Indore Department of Chemistry for our own work and sophisticated instrumentation facility, SIC IIT Indore, and CSIR for funding. This is the research group I have right now. About 8-9 students are working under me. And the work I have shown based on the work of the PhD students or Juan Shant, who is currently working on this kind of project in our laboratory. And I hope that this material will help us to keep our planet as beautiful as ever. This is the picture taken from moon to the earth, and it remains as such. We can manage to control the pollution, control the greenhouse effect, and we can make it a sustainable journey. Thank you for your hearing.
Thank you, sir. Dear participants, if you have any queries, kindly ask questions or kindly post your questions in chat box.
Okay, before you get the questions, I had a question for Professor.
Yes,
Right?
yes, please.
The hydrogen production which you are talking about using
Yes.
these porous materials,
Right.
how does it compare with the biological hydrogen production, which is also being used for clean hydrogen production? Because the reactions are similar to the photosynthetic reactions with biological organisms.
Absolutely true. And now you see that this production of the hydrogen using covalent organic framework is depending upon on the capturing of the light energy. And the amount of the light energy is getting captured and getting transmitted. The quantum efficiency is still quite low, in the tune of 0.16 or 0.2, something like that. However, in the biological case, it is more than that.
Yeah.
Nature has developed the system in the biological things by a million of years. And the scientists have just started to understand them and started to utilizing that. So it is still about to catch up. But I hope that with the kind of research going on around the world, and a lot of strays are getting now given for the coming up with alternative fuels and hydrogen as a cleaner fuel. So I hope that something will come up, but still it is not up to that level. Still it is not up to that.
Yeah, this reaction is wavelength dependent, right?
Right.
What is the wavelength here?
No, it depends upon on what materials you are using. Okay, so all the materials are not capturing the same wavelength, but mostly this covalent organic framework, being the organic compounds, they used to capture in the range of 500 nanometer to 400 nanometer. So that is the wavelength that is getting generally captured and utilized.
Yeah, because the advantage with photosynthesis is that there are multiple
right.
That capture many wavelengths and pull it together.
Absolutely.
So that may be increasing the efficiency of
that could be, but the system in the photosynthesis, that is in the chlorophyll, that is a quite complicated one, and there is a system of funneling the energy towards the reactive center. And the way it has been beautifully designed by the nature, that is quite a cumbersome task in the laboratory at this moment. But let us see what happens in future. That is what I can say at this moment.
Yeah, thank you.
There is no question in chat box. We will continue. Thank you, sir. It was a great pleasure for all of us to listen to you. Thank you once again.
Thank you.
Now I invite Dean Faculty of Sciences, including Forensic Science and Faculty of Agriculture, Dr. K. M. Guruprasad, to propose words of thanks. Please, sir.
Thank you, Madam Varsha. It was a great talk by Professor Suman Mukhopadhyay, enlightening us with the new researches in the area of porous materials and how they can be applied. And it was a very revealing fact for many of us, particularly people like me working in biological areas, to know that what are the chemical alternatives that can be used both for cleaning the environment and other pollutants, and also for generating hydrogen. So this is, as Professor Mukhopadhyay said, it is a developing field which is now coming up, and how far this will be applicable, but I feel that certainly for cleaning the environment, this may be a very useful way of using the material, and I believe this will be expanded to more and more applications in this field during the climate change, particularly to mitigate the climate change and reduce the CO2 content in the climate. So with these words, I thank Professor Mukhopadhyay, and I also thank the Vice Chancellor, Professor Upinder Dha, for encouraging the discussions and talks by inviting many people from other institutes through various platforms. And Science Club is one of those platforms through which we can come to know of emerging new areas of science and their applications. Thanks to Professor Mukhopadhyay once again. Thank you.
Thank you,
Thank you
sir.
very much.
Now I request everyone to rise for national anthem. Technical team, kindly play the AV.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you so much, everyone,
Thank you,
for
sir.
being here. Thank you, sir.
Thank you very much, Dr. Mukhopadhyay.
Thank you very much for the kind invitation. Thank you, madam.
Thank you.
sir.
Okay, thank you.